So let's see first from a part handling perspective, what are the guidelines? Simple guidelines, okay? We will just get exposed to. It's not a comprehensive set of guidelines. This is similar to the example that we saw. What it says is, this particular design is asymmetric and this particular design is symmetric. Which one would you choose from a designer perspective? You would choose this because for this particular stuff you need visionary inspection, or you should be able to feel it which side it is. Okay, that's one thing. Design with end-to-end symmetry or rotational symmetry. There are two things here, right? If you take an axis here, that is one symmetry, and this symmetry, it is also rotational symmetry, correct? This is like a difference between a nail and a screw. Is there a particular angle in which you put a nail? A nail is a nail. You want to put it here, you just put it there. Okay. But then when you put a screw, you want to use a screwdriver. The screwdriver has to be correctly inserted on the edge, right? Whereas the hammer can directly go on the nail at any point. You cannot say the hammer should exactly go only in this particular line. No. It just goes on the head of the nail, it's fine. There's a difference between the nail and the screw in handling and insertion perspective. Okay, of course, they do two different jobs. In a very large outset, they actually fasten two different components, both the screw and the nail. They fasten two different components. Okay. The second one is about, it's again symmetric, but what it says is slightly asymmetrical versus pronounced asymmetrical. What this guideline tells you is, if you cannot make it symmetric, make it pronounced asymmetric. Don't make it like this. It is actually asymmetric. This design is actually asymmetric, but it requires very careful investigation to find out in which direction it is asymmetric. Because this is going to go and sit on another part. You imagine that there are going to be 4 pillars on which this is going to sit. You will have to look at it and properly align. Okay. So what this says is, you kind of show a pronounced asymmetry, or you kind of have an indication here that this side will sit on this for sure. If symmetry can't be achieved, make it obviously asymmetric. Okay. So that is a guideline. The third one, I'm just showing the picture. You get an idea? What is this?
Fix anything in a particular direction.
Fix anything in a particular direction. What does this look like? Cap. Have you guys come across thermoform cups? Not the paper cups, thermoform cups. And they stuck one on each other. Or you have seen stainless steel tumblers in the anywhere in the hotels. Okay, if you see, majority of the places, they don't put them one into the other. There is an issue. Sometimes they go and get stuck. They are like this. They are like this. So you can put another stuff on this like this. And then you can keep building this. You can look at the chairs. You remember the plastic chairs that we use, one on top of each other. These are designed carefully, okay, but then there are some designs where you put it, you will never be able to remove them. This is what this idea says. You need to have a projection that will save you from jamming when you store them. Okay, it won't let it go beyond a particular level. The jamming happens because it goes all the way down and you are not able to pull it off. Okay, so hence you have this. Sorry? Yes. It will affect the cleaning. But these are majority. Sometimes what people argue is this is usually for the transportation purpose. Okay, these are stuff that you can eliminate at a later point. When you are going to use it, that part can be eliminated. Okay, this is for only for the transportation. This is some, in a similar sense, some guidelines. For instance, this one. Okay, if you're going to make many such components and you are shipping them, what could be a problem when you put so many of these together? Sorry? They will get tangled. They will do this. Multiple such. There could be another one that will get tangled like this, right? This might get tangled into something else. This might get tangled into something else. So then it becomes a problem. You need people to be able to remove these things. So instead, when you design, see, look at this. Your design, this is a perfect design from a design perspective. But from a transportation perspective, it is good to have such a design such that it does not go into through this. I'll tell you one guy, I don't know, did you guys meet, did Mr. C. Varadarajan spoke to any of you guys? No. There is one group that he spoke to. He's a pretty senior designer. He once told about washing machines. He said there is a limitation for the companies not to increase the height of a vertical axis washing machine. This you can see anywhere. You take a particular Samsung, you take Whirlpool, you take Godrej, and you look at all their vertical axis or horizontal axis, whatever, the front open or the top load, does not matter. All of them will be of the same height. Any guess? What? Sorry?
Anthropometric data.
No. I didn't mean to say that this height and that height. That is understandable, right? This height and this height also is not allowed. They all always, over the years, they all have stayed the same. Why? I was surprised. I don't know whether you will be surprised. The reason was the transportation. They have trucks, okay, that they have leased. The trucks were built for them, and they can only take whatever that height is, 3 or 4 washing machines when they are aligned. If you adjust it by few centimeters each of them, instead of 4, I can only take 3, which means in a container, let's say that 4 times, if I'm taking 100, so some 25 combinations are there, I can take 100 washing machines, I can take only 75 washing machines, which means 25% I'm losing directly there in terms of transportation. That they cannot allow that to happen. That's the amount of tolerance that they work on. So you can imagine, when I'm designing, I should know the transportation. That constraint comes into picture. Okay. So there is another interesting example. Okay. Cars. Have you seen how cars are taken from one place to another? Correct. So let's leave that. Let's come back to that. Okay. The glass that is used for the cars, okay, the front windshield and the back, these are all the toughened glasses. Okay. So people said that this needs to be of this quality, the toughened glass. Okay. Highest toughened glass in the front. So is the case at the back also. So one designer had a question on why the front one. I understand, because it is going in this direction and there's a lot of the air hits the front one, right? So you need to have a really toughened glass there. But why do you need to have a toughened glass at the back? This is purely from a performance perspective. This is not going to save you from burglary and all that. Today people can break even those toughened glasses, right? These are purely from a win perspective. Okay. But the company said, no, we need to have toughened glasses. They had a reason. Can you imagine what the reason is? Because see, wind, I understand. You will get wind from the front when you drive, and sometimes in the side, sometimes. Okay, but not as much as you get from the front. Why do you need an equivalent toughened glass at the back? You have an answer?
Just like maybe cyclone winds.
Even in the cyclone stuff, the cyclone is going to come from the back. But in the cyclone, your entire car will get lost. Let's not worry about the windshield. If it's a cyclone, your entire car is gone, right? So windshield is not going to save you.
Maybe it's got something to do with the threshold of the impact that can happen on the car.
See, they are not structural members. You talk about the frontal portion, you talk about your back portion, you talk about your seats. They are all structural members. They will affect in terms of impact. But these are not load bearing. They are only for visibility and to prevent the wind. That's all. These are the only two purposes of your glass. That's it. They are not structural members. In terms of impact, what they are designed in such a way that they will break into small pieces and go such that they will not hurt the occupant. That's all. They are not structural members. They are not designed to save you under an impact. It's related to the point that I raised first. Do you know how they are shipped? Not all the cars are taken in the frontal direction. They are actually also on the truck, they are parked in the reverse direction. So you never know which one will be parked in the reverse direction, which one will be parked in the frontal direction. Okay? This is an example where you need to know even how a particular car will be transported. Let's say that these divisions were entirely different and there was no feedback. That car company will probably, shut down in probably a year's time. Okay, because that's why they record failures, modes of failure they record. Okay, today we have a watch company which comes back and asks us that there are 120 checkpoints. In spite of that, we are having these many losses in our stuff. So we need to figure out where the problem is. Okay, their mechanism is fine when it gets out of their shop. Okay, there's nothing wrong about it. They have had a very nice protocol to check it. There's no question about that. Somewhere in between, there is a problem. It could be the shipping problem. It could be the the packaging problem. It could be the how they get it down from the truck load, unload it, and how they put it in the showroom. There are different. So they want an FMEA done on that to understand where the fuse is. Okay, these are interesting problems if you look at it. So the point is, one need to be. This is the challenge for a product company, right? So it's not just that I build a product and I send it off. No, you need to establish the entire chain. It needs to be shipped like this. It needs to be handled like this. It needs to be showcased like this. It needs to be handed over to the person like this. Subject to all the uncertainties. Performance-wise, there is another problem. Until you hand it over to them, and performance-wise, there is going to be other sorts of problems as well. Okay. So anyway, so these are, for instance, from a design perspective, there is nothing wrong about it. But from a transportation perspective, it is useful to have it this way so that they don't tangle. Try avoiding stuff that are very small, that are slippery. If you try to design something like this, maybe with sharp edges, like a square, like a cube rather than a sphere, because it is always easier to handle a cube than at this level. That's why the fingers are also given. Okay, and then not to have a sharp design, flexible design. If you cannot avoid any of these situations, then proper handling needs to be advised. You cannot use the fingers because you will end up hurting your fingers. As simple. If you remember, one of the best practices in the product design lab is to, you never know who's going to put what. Okay, it might not be your fault. You just turned around and that guy was doing something, you hit his elbow, they were tightening something, that went and fell outside the desk, it will land like this on the other guy's foot. So that's why we insist, and we always even send you back, I guess, okay, unless you had some big like wound and then you had plaster around your foot. We never allowed, at least in my PD lab, I made sure that people don't sneak in with a floaters or a flip-flop or whatever sandals. It should be toe covered. That is our point. Okay, I immediately get reminded of the toe injury always. Okay, anyway, and then you can see, you go to a hotel, there is a best practice, people always wear a hair cap, because one of the major things that you can always see, don't ask me whether that saves, okay, it does reduce it for sure, okay, because this is something that is out of your control, you don't even know, okay, then it comes in, right? So yeah, and then there are multiple things like that. Earlier people used to, small digression, but then earlier they used to bring the glasses from inside with water, right? So they will put their fingers and then they will bring it like that. Okay? But today, now you see, they will keep the glass and then they will pour the water. The water is always there for you. They will only come and refill the water. There is no way by you to, with all due respects to the server. Okay, but the point is they touch multiple things. So anyway, it's not going to be as clean as the water that day. Okay, so that is the best practice. If you look at it, best practices are there at all places. Okay. See, best practices is not necessarily only for doing good. In an ad hoc manner also, for doing something, there is a best practice. Okay. Okay. So avoid pots that stick together, that are slippery in nature, they are very delicate, that are flexible, they are very small or very large. Okay. But it is not applicable in general. Let's say that you are looking at flexible electronics, then it needs to be flexible. Okay, today there is a pressure sensor that you want to do. It is flexible. You hold it like that. It will be only flexible. But these are general guidelines. Okay, if the nature is that, yes, it's a nature is this. Diamond can only be like this. Diamond cannot be like this. Diamond can only be small. Then you need to have appropriate handling techniques. That's what it is. Diamond can be like this, but then you need to be a country to hold that, right? You cannot be an individual to have. Anyway, so the one thing is, the first one, as I pointed out, is this is done. Now we have finished talking about handling. Now we need to talk about the insertion, okay, so that it becomes a assembly. From this, can you imagine what might be there in this slide? Guideline. What guideline can you think about? The orientation. Good. That in one sense we talked about it already. Then insertion. Anything else? We'll see. So you want to assemble. Okay, this guy is going to go and sit inside this. Okay, but there is a problem. I want this guy to sit here, but he got jammed here. What could be a potential solution? Sorry? Tilting is further. No, this is jammed. You see, when I say jammed, what it means, it got stuck. Sorry? Round edges will might help, not always, because it usually gets stuck here. You understand, right, what is happening here? Yeah. Then, sorry, someone said something else. You can have a guide, I understand. Guide on the sides you can have, and then you push it so that it will pass through that. Now, one of the best guide example is your calculator, if at all you guys used calculator. Okay, the calculator cover has a guide, so it will go on that. What is the other one? Hole. Hole. You said where?
All for the inserting part.
For the part that is being inserted. Where?
If a cylindrical guide
So that you can put your finger and remove it. Why do you need that?
cylindrical guide is kept like a calculator.
Oh, you mean to say that you will have something like this?
Yeah.
No. That will affect your design in general. Yeah, fine. Okay.
Calculators like they have along with the guidelines on the other components they all have some cavity where the guidelines fit.
Oh, okay.
Yeah, that's what you trying to.
Okay, fine. Okay. Okay. So I'll show all the three cases, then we'll look at the solution. Okay. There is an insertion difficulty in such a case when you are trying to do that. Why? If you know why, you know the solution. So there is a hole and I'm trying to push something inside this. It could even be a screw. But beyond a particular level, it's very difficult. Air could be trapped. Air trap. This is actually a major research area. Unimaginable. Huh? Okay. So what could be a solution? That is too much. Every hole that you try to screw, you go and like vacuum and then you do. Yeah. It's not like air means it's not like so much air, right? It's only like this particular space. So you just need some space for this guy to squeeze in. So what you do is you just put a hole in the screw itself. There are several screws. You can see that there will be a hole. You can see that. Okay. Well-made screws will have those holes because it's not easy to put a hole in the threaded screw, and those screws are naturally expensive than the regular screws that you look at. Okay. You see the problem in this? This is a nice problem. You see the problem, right? This is the hole. And I'm trying to insert this guy to this guy. He is designed perfectly.
Perfect.
What is the problem?
There should be more dimension should be more than
Which one should be more?
the whole diameter should be more than the inserting part. At least by
No, you want a fastening kind of a stuff, no? So the fit wise, it's still the snug fit kind of a stuff.
like press fit 0.1 mm, 0.2
Mm. Fine. But the deal is this.
shape of the edges.
What you are talking about is this. I'm talking about this. You get the point. The axes that we are talking about are different. Your snug fit and all that comes from this axis. I'm talking about this. The length. The length is pakka. Only this much it is designed. Correct? Have you ever had the problem where your thread mismatched? There is a thread inside and then you put the screw and then it got mismatched. It will not go beyond a particular stuff. Something of that sort could happen in this. Okay, instead of putting it right exactly here, a small tilt will mean that this guy, will mean that it is like this. It will end up being like this. What could be a potential solution for this? Sorry?
Gravity can
Sorry, one at a time. Sorry. Slope where?
Front is to be there.
Here you will have a slope. Huh? No, the slope will not help you. Nah. You are saying this, right? Yeah, but still this length is still the same. I mean, I have almost given the solution. I gave the solution when he answered. Yeah. You said something. Same, huh? I don't have a problem in entering. Even with this, with whatever you are telling, the slope or the cuttage and all that, I might still have the same problem. I'm not addressing the problem. You had a solution?
It can be like the diameter for the entering part with this part enters.
The
that can be larger and the other end can be smaller, so it can clearly fit through.
How come? How can it be larger here? It cannot be larger here.
No, I mean the shape can be like this. So
Okay, I don't know whether you guys appreciate the problem. The problem is not this not being able to go into it. That is fine. I never said that there is a problem with these dimensions. It's fine. The problem is this length is so well designed to this length here. For a small mismatch also, I might get locked. Okay, so we'll see what the solutions are. This one, you design it in such a way so that you still have control from outside. That's one thing. Or guidelines. See, many of the solutions that we'll discuss in the rest of this course is not unique. There are always other solutions that are available. Okay, these are textbook solutions that are taken off the textbook. So in such a case, the part cannot jam. Okay, hole in the workpiece, not on the screw. Or, I mean, if it's a screw, you can have a hole. Otherwise, it's a hole on the workpiece itself for it to release. That's one thing. In this, it's simple. You just increase the length of this guy. That's all. Okay. So what is happening is you are able to reach out a little bit, and then of course you need to have this hole. You need to have the scope to have a longer hole, so that I push this. You understand, right? This hole is not dependent on this size. Let's say for design purpose, you wanted this guy to be the same. Okay, but from an assembly perspective, you need this guy to be longer. So this second level hole should be longer. That oftentimes you will be able to do. Then you will not have this issue. Okay, because it will get inserted first, and then you keep driving it, then automatically this part will get fastened. Yeah. So what you try to look at is little or no resistance during insertion. So this will be, it will be no resistance. It will be, you should do it in such a way that there is little resistance. Okay. He kept pointing out to this, provide chamfers to guide insertion of two mating parts. Whenever there are two parts that are trying to mate, you might want to have chamfers that will align with each other. We have discussed a lot of guidelines right now in terms of insertion, handling. Do these really help? If so, how? Because these are just a bunch of guidelines, right? There are like some, I don't know, 5 plus 3 we discussed, and these could be specific also.
It's for damage.
What?
Avoid damage during assembly.
Okay.
the standardized things, so maybe two different things.
Yeah. So the idea of this question is, how do you convert this into knowledge? These are some information that you have. How do you convert this into a knowledge so that you can systematically deploy them? The other stuff is, this does not provide a quantitative measure for the ease of assembly. It does not give you a relative ranking to suggest which guideline might result in handling and assembly improvement. That's what I said. There could be multiple things, right? So which one would you choose? Because you always wanted to reduce the cost or time or whatever that thing is, right? Efficiency perspective. And again, this does not give you a perspective on, can I eliminate a particular component, or can I think of it from redesigning a particular part? This does not give you a guideline yet. It just says, if you have this condition, you do this. So then, if you have a particular problem, you need to go through all the conditions and figure out, okay, that 102nd was my condition. Okay. Eventually, these are just a set of rules that needs to be followed. That again, you need to be there to understand these problems over the years. And usually, a designer with this background is better than the one without this. So basically, you are trying to, imbibe the legacy instead of an expert, you might want to imbibe the knowledge. That's not what we want. Instead, what we want is an approach that offers a designer, just like a funnel element tool or something, with an organized method to design a product for easy assembly. You should be able to evaluate the assembly before going into production, be able to compare it with competing designs. These are the things that we want to do, and that's what essentially DFMA does. So what it does is it tries to quantify all of these simple guidelines that we saw and much more guidelines, and it will try to quantify all that such that finally it will give you a number so that you can compare 9 versus 10 and you are not comparing A versus B. So today we'll wrap it up with this.